Dear students and viewers, hello, I am Kudsiya Gani. I teach physics at a Srinagar-based government college. Today we are going to discuss about Paulis Exclusion principle. This is a topic that pertains to the 5th semester students of physics. Dear students, I want to tell you that in your previous semesters you have learnt in detail about the classification of particles as fermions and bosons. Fermions and bosons. Fermions are half-integer spin particles. They obey Fermi-Dirac statistics. And bosons are zero or integer spin particles. And they obey Bose-Einstein statistics. Fermions include protons, neutrons, electrons, neutrinos, mostly the subatomic particles. And bosons include gas molecules, photons, say helium atoms, alpha particles, and so on. You have also learned that quantum mechanics is fairly applicable across all realms from microscopic to microscopic domain. The only thing is that its manifestations, its implications become dramatic, they become visibly clear in the subatomic domain. An important quantum mechanical principle that we are going to learn today, to discuss today, is Paulis exclusion principle. Paulis exclusion principle. It was given by Wolfgang Pauli, W.G. Pauli, in 1925, an Austrian scientist, physicist, therefore the name Paulis exclusion principle. Remember that Paulis exclusion principle is applicable to fermions only and not to bosons. Of course, there are some other principles that govern the physics of bosons, but today we are going to discuss in particular about fermions through the concept of Paulis exclusion principle. Now, what does the principle state? It states that no two electrons in an atom can exist in the same quantum state. In other words, different electrons in an atom exist in different quantum states, but not in the same quantum state. Now, let us try to gradually build this concept, both from the point of view of mathematical description and then a physical interpretation, and then let us also go to the ideas that actually struck the mind of Pauli that made him conclude this way. So, we'll try to gradually build the concept. So, suppose you have a system of n non-interacting particles. Whose wave function is given by psi. So we can choose to write it this way: psi of 1, 2, 3, so on up to n is equal to psi of 1, psi of 2, psi of 3, so on up to psi n. Now, for the sake of simplicity, let us choose only two particles. Particle 1 in the quantum state A and particle 2 in the quantum state B. Right? All of you are aware that this quantity psi square gives the probability density. That is the total probability of finding a particle in a given space. Therefore, we can choose to write psi of 1, 2 square times is the same thing as psi of 2, 1. This also follows from the fact that we treat particles essentially as identical particles. Whether we approach the system from a classical point of view or from a quantum mechanical point of view, we treat these subatomic particles, these small side particles, as identical particles. And because the particles are identical, it doesn't matter if the position of one is exchanged for other or vice versa. Therefore, the probability density psi square term will essentially remain the same. However, from this equation, there are two conditions that follow. One is that psi of 1, 2 can be the same thing as psi of 2, 1, or psi of 1, 2 can be minus times psi of 2, 1. That remains to be seen. We will follow that in the next discussion. Now, let us carry forth the discussion in this way. Suppose the particle 1, which is in quantum state A, and particle 2 which is in quantum state B, together represent the wave function of the system. So, there can be two cases of representing the same. Psi 1 will be given by product of psi of 1 in the quantum state A and psi of 2 in the quantum state B. In an equally likely possible approach, we can also write psi of 2 is equal to psi of 1 in the quantum state B and psi of 2 in the quantum state A. Right? Again, coming to the fact that particles are treated as identical, it doesn't matter that if one is exchanged for the other will give us a new result. So, to say that in which configuration does the system have a likelihood to occur, we cannot say. But a best description, a best judgment would be that the system has an equal likelihood to occur in either of the configuration whose wave function is represented by psi 1 and the configuration whose wave function is represented by psi 2. Therefore, a most reasonable description would be to say that the system exists in a linear combination of these two wave functions. So, we can write in that case, again we have two cases. One is to add them up and another is to subtract them. So, we can choose to write that the system has a likelihood, has an equal likelihood to occur in either of the configurations on account of the fact that particles are identical. Therefore, the most reasonable description would be that we represent it by means of a linear combination of psi 1 and psi 2. In that case, we get two cases. One is psi s, symmetric wave function, that will be given by psi 1 plus psi 2, and antisymmetric will be given by psi of 1 minus psi of 2. So, let us choose to write it in terms of what we have obtained. So, psi s is 1 by root 2 times psi a of 1, psi b of 2 plus psi a of 2 and psi b of 1. Similarly, psi antisymmetric can be written as 1 by root 2 psi a of 1, psi b of 2 minus psi a of 2, psi b of 1. I hope you understand that this factor of 1 by root 2 comes from the concept of normalization. When we square and add them up, it comes out to be equal to 1. Now, obviously, there are some distinctions between the wave function that is symmetric and the wave function that is antisymmetric. There is also a hell lot of distinction between the properties of the particles that have symmetric wave function and the properties of the particles that have antisymmetric wave function. But one obvious distinction is that if we choose to make the two quantum states identical, that is, if we replace B by A, what do we get? We see that this psi is symmetric, it survives, but this psi antisymmetric, it doesn't survive. So, this is how mathematically we conclude that no two electrons can exist in the same quantum state. This is the mathematical description of the same. So, we have learned that if is A equal to B, psi antisymmetric vanishes. But that's not acceptable because we know that this wave function is surely representing a real existing system. So, this psi antisymmetric cannot be 0. We have to conclude the other way around, and that is no two particles, no two electrons in an atom exist in the same quantum state. So, we cannot choose to make A equal to B, at least in the antisymmetric case. Now, let us go to the physical interpretation of the same. What had Pauli But it struck his mind to conclude this way. See, let's choose an example of three elements, those of atomic number 9, 10 and 11. 9 represents fluorine, which is a chemically active halogen. All of you know that. 10 represents neon, which is an inert, inactive noble gas. And 11 represents sodium, which is an alkali metal with absolutely different properties. So we understand that by mere addition of one electron at each step, there is a sharp change, a drastic change in the chemical properties in the behavior of elements. And this cannot be true if all the electrons or even a handful of electrons in an atom are in the same quantum state. This does lead us to conclude that the atoms in these electrons in an atom are existing in different discrete quantum states, due to which there is a sharp change in their properties even when one electron is added from one step to another. Number one, now how do we infer or how do we determine the quantum states of an atom? One easy method, one easy way of determining the quantum states of an atom is to observe their atomic spectra. In the atomic spectra of all elements, remember students, in the atomic spectra of all elements, of course other than hydrogen because that carries only single electron, forget about it. But in the atomic spectra of rest of the all elements, we see that there are certain spectral lines that are missing. And these lines reflect the transition between two states having same quantum numbers. These were the unobserved, as Pauli had called them, unobserved lines. And unobserved lines correspond to those transitions in which an electron will have to move from one similar to another quantum state of same set of quantum numbers. So this is another logical reason that made us believe this way, and that I think that gives you a fair idea of Pauli exclusion principle. That's all.